Never ever try to make procedural generation without knowing what recursion is first. Recursion in Luau, or in general programming, is when a function calls upon itself multiple times to create solutions for smaller problems using smaller inputs. That being said, recursion is just we take one function and one input, and then we make it smaller, and we call that function in the function in itself, and then make that make it smaller, and we keep breaking it down into smaller chunks until we get our solution to our problem. Now, recursion needs two different steps before we make anything in our function. We need to have a base case, so we need to say a case in which we stop the function, and then we need to have a recursive step that keeps calling the function. And I'm going to show you guys how this looks like visually and in code in a second. But you have to understand that recursion, even though most of the time you're not going to use loops for recursion, you can still have an infinite loop and exhaust the Roblox engine. So you want to be careful with that, and you want to make sure you have some sort of case where you stop the function. Now, that being said, enough yapping. Here's an actual visual demonstration of what we're going to be doing. Now, right here, I have these parts from the top, and then it slowly gets smaller, and the positioning goes down and down until we reach the final case right here. This is our end case. Now, in here, through our code, this is all in one function within about 15 lines of code. We literally just take a part, we throw in three parameters, or three arguments, and it keeps getting smaller and smaller over and over until we reach a certain point. And I'm going to show you guys that right here. Now, we have this function create branch, and this is like creating a tree. This is my base case. And don't worry, we're going to be writing code together in a second. This is a little bit advanced, so I'm just showing you guys a brief demonstration. Now, this is our base case. We're saying if our depth that we're going to be passing into here is less than or equal to 0, then we can simply stop the function from calling itself ever again. It will never come down here. Now, then if we pass this case, well, this is our recursive case. This is us making new stuff within our function. This is our recursive steps. And what we're doing here is we're going to be calling the part, or we're going to be making a new part, setting the size to the length that we have up here, positioning it where we position, and of course we have to anchor it, and then our top is our position, plus a new vector is our offset of the length. This is just a way to get it from top to bottom, coming down here. Then right here, we're going to call the function that's right inside the function. We're going to pass in the position, our top position, so the position of our part, we're going to add 1 on the x-axis to slowly move it to the right, and then the length is going to be that same length and then multiplied by 0.7, so 70% of the original length. And then you're going to see how it keeps getting thinner and thinner as it goes up. Sorry, this is top to bottom, or bottom to top. It goes from here all the way up here. Then, from there, the depth is going to keep reducing by 1. And then right here, we first create our original branch at the position of the origin of the workspace. So at 0, 0, 0, our length is originally 10, and then our depth is 5. And then once we reach 0 for our depth, then we're simply going to stop calling this function. And we call the function every time with a new depth. That we keep reducing the depth by 1. So basically the function gets called however many times we specified our depth. This is our n minus 1 right here. And 1, 2, 3, 4, 5. We called it 5 times. And this is what happened every single time. So instead of saying if and then else and it's a whole different thing, we can just simply do something like this. And that's a nice little visual demonstration of how this is actually going to look. And let's write something pretty simple for now. But before we do that, actually, I want to show you guys some use cases. So let's search the workspace using recursion. So I'm going to pull out the output. And then what I'm going to do is I'm going to make a function to search the workspace, all its children, using recursion. Now, in Roblox, we do provide us sources to do this without doing recursion. But this is just for the sake of the video. We're going to be using recursion for this. So let's make a function called search object, and it's going to take in some sort of element, and I'm going to call this object, and I'm going to type check this to be, let's just say instance, right? It can be anything. It can be any object as long as it has children. In this case, I'm going to call search object, and the object is going to be the workspace. I just want to get every single thing in the workspace. Then what's going to happen here is we're going to say for I child in our object. So this can be anything. In this case, we're checking the workspace. Get all the children. Now, I know we said in recursion we're not going to be using loops a lot, but in some cases we might use a while or a for loop. Now, the base case here is we're saying that depth is less than or equal to 0, then we can stop the function. In this case, our base case is the for loop. What I mean by this is that we know for loops automatically will stop the loop once we get to a certain amount of or the last index in this table right here. So since we're looping through it like this, through what's it called, key values? There's a hash table, a different thing. We're saying our key and then our value in this table, which is the get children. Get children makes all this into a table, everything in the workspace. Once we get to the last object or child in here, the function will stop by itself, and in that case, that is our base case, if that makes sense. I know that might sound a little weird at first, like a lot in your head, but the function will stop calling itself once we get to the last child. So this is kind of our base case. Now, in a while loop, it would be something like while not, and then that would be the base case usually. Or you can add in an if statement to break it as well as another case. But in this case, man, I'm saying case a lot. In this scenario, the for loop will end by itself, and we don't have to worry about exhausting the Roblox engine with an infinite loop because the for loop is not infinite. A for loop is not an infinite loop because we know how many times we need to iterate, right? So now we can say we're going to simply say print out child.name just so we can see it. And then I should have made some cool printing, to like print out a tree or something. But it's cool. So then we print out the child.name and we're gonna search the object of the child. So we're gonna call this function, but on the child. So this is what we're going to be doing here instead of the same object. That way, because the child is a smaller input, if that makes sense, how I said earlier, we need to make sure it keeps getting smaller and smaller. In this case, it's not it's a child, so it's gonna keep going through each children. And in that case, instead of like with numbers, it's easier. But in this scenario, you can think of the object right here. This is the parent, the child, obviously. And for each child, it's gonna keep going down the hierarchy of the next child, and those next childs we can like pretend that it's a smaller input, but it's not a smaller input, it's more of just going more and more down the hierarchy, if that makes sense, right? Because we keep traversing our table over and over until we finally reach the end. So in this case, we need to keep going through each child, and thankfully, because this value will always change depending on which object, for example base plate right here, if I call this on this base plate I have right here, the next child, when we search it, is going to be the texture and not the base plate or the workspace. So it's going to keep doing that until we reach, well, nothing again, right? Because there's nothing to loop through, which is guarded by our for loop, which is nice. So enough yapping. Let's just see how this looks like in, I never actually stopped running. Let's just see how this looks like when we press play. And we should print out about everything in the workspace. So yeah, camera. This is from the bindable, but this is from my script. I'm just gonna make sure this comes up a little bit more. Kill brick, part terrain. It literally prints out every single thing. And there's 5 of these kill bricks. That's how Luau does it. So yeah, it literally prints out everything inside of the workspace, just like that. Now you could just say, well, why don't we just print out workspace get children? Yeah, we can do that. But this worked as well, and it printed out everything. And obviously, in regular cases, you're not going to be using it just to print. This is just for a demonstration. This would be something. Oh shit! Did I delete the workspace? Oh no, I deleted the script. Okay, thank God. I was about to say. But in other cases, this is you wouldn't be using it just to print. That's useless. You would use it to highlight certain nodes or something like that, or you would use it, or maybe you want to use it to find stuff for you as a developer. Just to keep searching over and over to find something. Maybe you're looking for a for example, a sound, and you forgot what sound, so you're looking for a sound, and you're saying if child is equal to, I don't know, this name, and then you just stop the function right there, and you can that's another case right there, to traverse. But um, yeah, that's a pretty basic use case of that. So another really nice use case of excuse me, another really nice use case of recursion is something like a countdown, which I know a lot of people have. This is like probably the most applicable. So I'm gonna call this number, just because it's a countdown for your game. So we're gonna say if n is equal to 0, this is our base case. Then I'm gonna say base case. Then we can simply return 0, right? And then else, this is our recursion case. So then right here we can just print out n. We can wait half a second between each time we slowly decrement the counter, and then we can say countdown n minus 1. We can keep counting down. Now, the way this kind of will look like is something like this. Or matter of fact, I'll show you in a second how that's gonna look like in a different function. But yeah, we just output. We just literally just look at it right here, and then we will see that it will print out. Oh, I never even called it. I'm tripping. So yeah, I'm gonna just call this countdown, and we're gonna start from Let's start from 5, right? So it's gonna count down pretty fast. And then right here. It starts at 5, 4, 3, 2, 1, and then there you go. And if you wanted to say 0, because we pressed right here 0, what we can do is we can print out n down here instead. Well, no, because it returned, so just put it right here, and then you can just print it up here as well, or you can print it all the way up here, right? Instead, that would make a lot more sense. But because it comes after, so I'm gonna actually keep it right here. But yeah, it'll start at 5, right? This function will start at 5. Then, once it gets down to here, it's going to call the function one more time. So then it's going to become countdown of 4, and then 3, and then 2, and it's going to keep getting smaller and smaller until we reach 0 finally. Now, another great example of recursion this is probably the most applicable one, is factorials. So if you guys don't know what factorials are, well, this is what a factorial looks like. And what this means is literally just 5 times 4 times 3 times 2 times 1. And if you don't realize, our base case is, well, if we reach 1, then we don't need to keep multiplying. And it keeps getting smaller and smaller, n minus 1, until we reach 1. So we can actually just see the factorial right here. So we can say factorial, and then of any number, right? And then what we can do right here is we can say is if n is equal to 1, then return n, or 1. Else, or then we can just say n times the factorial of n minus 1. Now it's very important to make sure you say n minus 1 here, because remember, we need to slowly keep making our inputs smaller and smaller, right? That way we can actually reach the base case. That's so we can solve our problem. That's what we're doing here. And this only works because we actually return some sort of number. Because remember, if we return in a function, well, then the function is able to be used as a variable, and it stores that in memory, or the value of that in memory. So we're actually able to use the number of the previous and then multiply it, or the given number, and then multiply it by the previous number added, and then subtracted by 1. It's going to keep getting smaller and smaller. So I'll show you how this looks like through a comment. So it'll literally be just like, let's say we say factorial of 3. And I'm actually going to just say this. And then we can just, I guess we can print it. And because it returns, I mean, yeah, but we can demonstrate the code. I think we all know the factorial of 3. It's 6 here. But then, yeah, so let's say factorial of 3. This will turn into, and I'm going to use an arrow just so it looks nicer. It'll literally, the first time it calls, it'll be 3 times factorial of 2. And then one more time, 3 times 2 times factorial of 1. Now remember, that first case, our n right here is 3. So right here, 3 times factorial of 2. And now what is the factorial of 2? What's it going to give us back? 3 times 2. So now n is 2 now in this case, because we're in the call stack here. We keep calling over and over. And then it's going to multiply that by the factorial of 1, which is 2 minus 1, which is 1. Then it's going to turn into 3 times 2 times 1 times factorial of 0. And it's going to keep doing this over and over. And then it's going to turn into 3 times 2 times 1, which turns into 6. And this is exactly how it looks like through recursion. This is how recursion looks like. Now, you might be asking, how the hell does this even work? How did this go from n times the factorial of n minus 1 into this? The reason why this can work is because our well, good for us, in memory, it actually stores our factorials, our values right here that we called, in memory. And then it keeps track of that, and then it makes sure to store it in some sort of memory address, so it keeps track, and then so we can return it one more time to use it again, if that kind of makes sense. It's a little weird, but yeah, recursion is weird as hell in general. Sometimes it can be really slow. It can take a lot of memory. I know this is a little of a more confusing topic for most people, especially for using it, but it's really good for using it for like a decision tree. So like object-oriented programming. Let's say you're making an NPC AI system, right? It's really good to traverse like this using pathfinding and whatnot. It's also good for some sort of algorithms as well, like quick sort, merge sort, and whatnot. Those is a whole different thing, though. And yeah, so yeah, this right here, this process is called the call stack, by the way. It just a way to visualize this is a box, and it just keeps getting smaller. I'm not gonna draw a full square, but it just keeps getting smaller and smaller like this, just like this, until it reaches the final, and then it's done right here. I can't even put a comment anymore, just like that. That's exactly how recursion works. And sometimes it can get really, really slow, and sometimes it's very, very fast. So yeah, I hope you guys enjoyed today's video. A simple case in recursion. If you guys have any questions, just let me know. If you're still confused or stuff up, just hop in my Discord, talk to me. I try to answer to every single comment. So yeah, that'll be it for today's video. I'll see you guys next one. Bye bye.